Hello, this is Miraj Patel, and today we're going to wrap up Unit 1 by talking about the metric system, scientific notation, accuracy versus precision, and some other small stuff. And before I begin, I would like to thank Miss Harper for providing me with these PowerPoints. And I also forgot to mention that in the past two videos before this, she also provided me the PowerPoints. So again, I'd like to thank her. And so today we're going to start by talking about the metric system. And so before we begin, there's three measurements. One for length, which is measured in meters, or the base. These are the base units, so meter. For volume, it's liters, and mass, it's grams. And here are some approximations of how much each of these metric units is in something familiar. And so the volume of 20 drops of liquid from like a pipette or a medicine dropper is about 1 milliliter. And um, 1 milliliter is 1 centimeter cubed, or as large as a sugar cube. And 1 gallon of milk has about twice the volume of a 2-liter soda bottle. So about approximately 1 gallon is about 4 liters, or 3.8 liters. And on toilets and other stuff in bathrooms, and they often say how much water is flushed, and so sometimes you could check that out. So, and about a 250 pound person weighs about 113 kilograms. And the way I like to remember is that about 1 kilogram is about 2 pounds. And converting between the metric system is pretty easy because all we have to do is move the decimals. And so here are the prefixes that we have to know. So K stands for kilo. These two we don't have to remember, but for your information, hecto is 100 and deca is tens, but you don't have to know these. These are the base units, so M is for meter, L is for liter, G is for gram. Those are the base units. Then uh, the D stands for deci, which is a tenth, centi, which is a hundredth, and milli, which is a thousandth. And these are all prefixes except the middle, which is just a base unit. And so all you have to do is, for the decimal mover trick, is to find where your number goes. So this is milli, so you would put in the milli spot, and count how many places you have to move the decimal to get to the unit you want to get to. So if you have 120 milligrams, you'd first find the milli spot right here, and you want to move to grams, so you count the boxes you moved, so 1, 2, 3, 3 spots, and then you go to the number, so you had 120 here, and then move the decimal place 1, 2, 3 spots, just like you did with the boxes. 1, 2, 3, and that's your answer. And so here are some more problems. So first, you have to find the prefix in this box diagram. So C, so you go to centi spot. So 15 centimeters, and you want to go to meters. So here's centi, and you want to go to meters here, not to get confused with milli. So because this stands for milli, not meters. So you move C to M. So you move 1, 2, 2 spaces. So you move the decimal place, which is here, assumed. 1, 2 spaces, and that will be your answer, 0.15 meters. And same thing with this one. So 7.38 kilograms to grams, so you find the kilo spot, which is all the way over here, and you move the decimal place 1, 2, 3, 3 spaces to the right to get to grams. So it's 1, 2, 3, so it's 7,380 grams and 7.38 kilograms. And you have 607 milliliters, and you want to get to liters. So you first find the milli spot, which is over here, and move it till you get to liters. So you have to move it one, two, three spaces to the left. So move the decimal one, two, three spaces to the left, and you get 0.607 liters. And same thing with the last one, 94.5 grams. And you want to move it to kilograms, so grams to kilograms is one, two, three spaces to the left. So you move the decimal place one, two, three spaces to the left, and you get 0.0945 kilograms. And here's a quick quiz to see what you learned from this PowerPoint. And so, which of the following is the base unit for mass? So let's just point out what all these base units are for. So A, meter, think about the 100-meter dash. You know, remember that they're running, so they're running a distance. They're not running volume, or they're not like running like a mass. So they're, just think of the 100-meter dash, so they're running a distance. And I'll just skip gram for now. And so think of liters when you drink soda. So soda, we measure soda in how much it holds. So, and then we don't worry about moles yet. That we'll find that out in the next unit. And so, and remember, grams are for weight. So just think of when you're like, if you have ever traveled before to like Europe or Asia, they everywhere else they measure in grams. So you have to remember, you have to make sure your bags weigh in kilograms. So think of weight in versus pounds. So just match. So just remember all these three these three units based on meter. Think of running like a 100-meter dash. Think of grams as when you're converting from kilograms and to pounds with luggage, and liters like think of a soda bottle. And how many milliliters are in 0.2 liters? So if we go back to the decimal moving trick chart, so you have 0.2 liters and you want to go to milliliters. So you have liters, so you move it one, two, three spaces to the right. And so you move the decimal one, two, three spaces to the right, and so you put in a zero if it moved farther. So you would get 200 milliliters if you move the decimal place three spaces to the right. And how many centigrams are in 1.34 grams? And again, so you start at grams, which just imagine the chart, and then there's deca, and then centi. So you'd have to move the decimal one, two spaces to the right, and you would get 134 centigrams in a gram, and in 1.34 grams. And that is how you convert it into scientific notation, which we'll talk about in just a second. And the next PowerPoint we're going to talk about today is about percent error measurements and like accuracy versus precision. And so before we start, a measurement is a unit or a quantity with a unit. And so all these would be examples of measurements because they have a number and a unit. Number, unit, number, unit. And scientific notation is a way of converting a really big number and a really small number and writing it in a shorter way. So just think of it as an abbreviation for numbers. And so the way you use scientific notation is you first have to move the decimal place so that there's only one digit in front of the decimal. So, and it's important to count it. So let's just do this one. So we have to move the decimal place so there's only one digit, one non-zero in front of the decimal. So we have to move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 digits, or we have to pass 11 zeros. And so then you first write the digit that you have, all the non-zeros, before and after that decimal where you moved it. So right now we moved the decimal from here to here, so there's only 2, so you don't have to really write the decimal spot if there's nothing behind it. And then you multiply it times 10, and you get that the number of zeros you skipped, and you raise 10 to that power. So let's just do this one. So first we have to move the decimal spot. So there's only one digit in front. So there's only one non-zero. So we have to just put the decimal right here. So you have to pass 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 zeros we have to pass. So, and so we first write the digit that's in front of the decimal, so 1, and then we multiply it times 10, and then we raise 10 to the exponent of the zeros we pass. So we passed 14 zeros in this one. And so that's the answer because we counted 14 zeros we passed, and we only had a 1 on the front of the decimal. And so the next problem, this is super small decimal, so that's how we get the negative exponent. So we have to do the same thing, count how many digits we have to pass until we get the decimal. So there's only one digit in front, so this 1. So we move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11 digits. So what's in front of the decimal? There's only a 1, so that's how you got the 1. And then you multiply times 10, and then we raise it to the number of zeros we passed, or digits. So we passed 3, 6, 9, 10, 11 digits. Excuse me there. And because it's a small number, it's negative. So think of negative for small. And right now we're going to talk about accuracy versus precision. And so if you think about it, accuracy is how accurate you are. So how close you are to the actual actual target. So this would be accurate because we are on target here. But is it precise too? Well, I'll tell you the definition for precise is how close the values, or in this case darts, are close to each other. So this would also be precise because the darts are near the same spot, or almost on the same spot. So what is this target? So is it accurate? Well, it's not on target, so it wouldn't be accurate, but is it precise? Yes, it is precise because the darts or values in science or something, or whatever you're doing, is close to each other. So this would be precise but not accurate. And what would this target be? It's not accurate because it's not on target, and it's not, neither is it precise because the values are all the way up far apart from each other. And so here are the answers like we just talked about. And here are the definitions so you can copy them down. Accuracy is how close the values are to the actual true value, and precision is how close the values are to each other. And so here is an example of a problem in science we can use accuracy and precision to describe. So the target is 1.59. So let's see if these three students were accurate and precise. So 1.59 is at target. So are any of these close to 1.59? Well, this one is super close. It's only 200ths off, so this would definitely be accurate. These two, however, aren't because they're way off. And is this precise? Well, 0.54, 0.6, and 0.57. I would say that's pretty precise. Like, it's close to each other. It's not that far off. But let's look at student B. So student B it's not accurate because we decided that we already compared 1.59 to 1.51 and 1.7. So neither of these two are accurate. But is this student precise? Well, 1.4, 1.68, and 1.45. Well, that data is all over the place, so this would neither be accurate nor precise. And so let's look at student C. Is this student accurate or precise? Well, we said that definitely they're not accurate, but let's see if they're precise. Well, it's 1.7, 1.69, and 1.71. They're only 1/100th off, so this student will be considered precise, but not accurate. And now this is an important thing, how to calculate percent error. So you do experimental minus true over true times 100. And this is used to calculate how far you are from accuracy, or how much percent off you are. And so this problem asks us, what is the percent error if the measurement is 99.1 degrees Celsius, but the actual temperature, the true temperature, is 100? So here first you have to write out the formula. So if you recall, it's experimental minus true over true times 100. So experimental is 99.1 minus true, which is 100, over true, which is 100, times 100%. And so you subtract these two, get 0.9 over 100 times 100. So, and the final answer will be 0.9%, and it's always positive, so that's why we have these absolute value marks. So this is never negative, and that's also important. So otherwise you would have got a negative answer, which is never true. So percent error is always positive. Remember that, always positive. And here's a quick quiz to see what you learned and which of the following expressions is not correctly changed to scientific notation. And so remember, you have to move the decimal place so there's only one non-zero in front of the decimal. So we have to move 1, 2, 3. So we write the little decimal number we have after we move the decimal first. So 4.56 is correct, and then multiply by 10 and raise it to the power of how many digits we have to pass. So we have to pass 1, 2, 3. So 3 would be correct, and it's negative because this is a small number. And so this is fine. So let's do the next one. So we have to move the decimal 1, 2, 3, 4, 5. 5 digits to get all the way over here. And this is a small number, so it's negative. And so we first write the number. So 2.54, that's a new number, times 10 to the negative fifth, which is correct because this is a small number, and we passed 5 digits to get there. So let's do C. So we have to move the decimal place, but this is a positive because it's a big number. So we have to move the decimal place 1, 2, 3, 4, 5, 6 digits we have to pass to get it into the right spot. So the new number is 8.426 because we have to write all the non-zeros, and then times 10 to the 6th because we passed 6 digits. So this is correct. So by process of elimination, we have to eliminate D, but why exactly is this incorrect? Well, if you move the decimal place, you would move it 1, 2, 3, 4 to get to the right spot, but this one only says 3. So that is why it's incorrect. And which of the measurements of a 2-gram object is most precise? Well, this question, you don't really need the two. You don't really need to know that the actual value is 2 grams. That would be only useful if we're trying to measure accuracy. So all we have to do is compare these numbers to each other and see how close they are. So 2 grams, 2.13, and 1.92. Those numbers are way far too off. And this is a set of answers. 2.1, 2, and 2.2. Those are also so far off because they're 0.1 off, which is a tenth of a gram, which is quite a bit. And C, 2.05, 2.04, and 2.05. Well, two of these even repeat, so, and this one is only 100th off, so C would be the most precise. And just to check, look at D, so 1.5, 2, and 2.5. Well, these are 0.5 of a gram off, which is quite a bit. That's like the most varying out of all of these. And so that is it for Unit 1. And thank you for listening to my video. I hope that helps you learn about some of the stuff for Unit 1. And don't be afraid to ask questions. And I hope you have a good day, and see you later.